Today, we're going to pull back the curtain on the architecture that powers pretty much everything you use online. We're talking about the journey from a simple, single application to the incredibly complex and resilient world of microservices.
You ever think about that? How can these massive, global applications serve millions of people at the exact same time, pushing updates constantly, and yet they just work? It's not magic, and it's definitely not luck. It's all about architecture. And by the time we're done here, you're going to know exactly how they pull it off.
All right, so our story has to start at the beginning, right? And for most apps, that beginning is a simple, all-in-one structure we call the monolith. It makes perfect sense when you're starting out, but, well, it has a hidden breaking point.
So, what is a monolith? Imagine you're building a car, but the engine, the wheels, the steering, the seats, everything is welded together into one giant, inseparable piece. That's a monolith. Everything lives in one place, one huge code base, one single deployment. Super simple and efficient at first, but then you get popular. What happens then?
Well, the first thing you try to do is just get a bigger car, right? A bigger server. We call this vertical scaling, but you hit a wall, and you hit it hard. First off, the price for those high-end super servers gets insane really fast. Second, you've just created one massive single point of failure. If that one machine hiccups, your entire app is just gone. Poof, offline. And finally, even the most powerful server in the world has a limit. It can get totally overwhelmed, and then the app slows to a crawl for everybody.
Okay, so making one thing bigger and bigger just doesn't work. The real solution was this totally revolutionary shift in thinking. Instead of building one giant thing, what if we broke it down into lots of tiny, independent pieces?
And this, right here, shows the difference perfectly. On the left, you've got the monolith, one giant application, one database for everything, all tangled together. You change one tiny thing, and you risk breaking the whole system. But on the right, that's the world of microservices. The app is now a collection of small, independent services. The service that handles payments doesn't need to know or care how the inventory service works. They're loosely coupled. They just talk to each other.
Now, this slide here, this is the golden rule. This is the one principle that makes the whole thing work. Every single microservice gets its own private database. This is totally non-negotiable. It ensures that they are truly independent. The payment service has its data, the shipping service has its data, and they are not allowed to touch each other's stuff directly. This is what finally breaks that tight coupling that caused so many problems with the monolith.
But, there's no free lunch. In solving that massive scaling problem, we've just created a brand new one, and it is a doozy. If every little service has its own data, how on earth do you keep everything consistent across the entire system? It's like we've slain one dragon only to find a much scarier one waiting for us.
Let's make this super real. You're online, you find something you want, and you click Buy Now. Behind the scenes, the payment service takes your money. Check. The inventory service reserves the item for you. Check. But then, the shipping service crashes. So, wait a second. What happens now? Have you just been charged for an item that is never going to ship? Is that item stuck in limbo forever? This, right here, is the distributed data challenge.
Now, the old school way of solving this was a protocol called a two-phase commit, or 2PC for short. You can think of it like a really strict traffic cop for transactions. It works by making sure every single service says, yes, I can do this, before anything is actually finalized. It absolutely guarantees consistency, but it comes at a massive, massive cost.
And here's why that cost is just too high for the apps we use today. 2PC is what we call blocking. While that coordinator is asking every service for permission, all of those services are just frozen, locked up, waiting. This creates huge delays. It's slow. And even worse, that coordinator, the traffic cop, is itself a single point of failure. If it goes down in the middle of a transaction, the services can be left locked and stuck forever. It just doesn't work at scale.
So to really get the modern solution, we have to first understand a fundamental law of the universe, or at least the universe of distributed systems. It's called the CAP theorem, and it basically lays out the hard choices that every single system architect has to make. Okay, first up in CAP is C, for consistency. This one's pretty straightforward. It just means that everybody, everywhere in the system sees the exact same, most up-to-date data at the exact same time. You post a picture, your friend on the other side of the world sees it instantly. That's consistency. Next, we have A for availability.
This means the system is always on, always ready to answer. You make a request, you get a response, period. It might not be the absolute latest, most up-to-the-millisecond data, but you will not get an error message. The lights are always on. And finally, we have P for partition tolerance. This one's not really a choice, it's just reality. It means your system has to be able to handle it when the network gets messy. Connections between servers drop all the time, a network partition happens. Partition tolerance means your system doesn't just fall over and die when this happens. For any real system on the internet, you must have P.
And here it is, the theorem itself, the big trade-off. In any distributed system that has to deal with network failures, which is all of them, you can pick only two of these three things. Since we just said partition tolerance is an optional, your real choice is between consistency and availability. You can be consistent, or you can be available when the network breaks. You cannot be both.
So let's look at what these choices actually mean. A CP system, like MongoDB or Spanner, chooses consistency. During a network failure, it might refuse to answer a request just to avoid the risk of giving you stale data. It sacrifices availability. On the other hand, an AP system, like Cassandra or DynamoDB, chooses availability. It will always give you an answer, even if it's slightly out of date for a few seconds. This idea is called eventual consistency. That C option, that's really the old monolith world, where you just pretend network failures don't exist. Okay, so armed with that knowledge, we know that modern, massive apps almost always choose availability. They embrace this idea of eventual consistency. So how do they manage that complex dance of data without everything falling apart? They use an incredibly elegant solution called the Saga pattern. So let's compare the old way with the new way. Two-phase commit was all about strong, immediate consistency. It was blocking, and it scaled terribly. Sagas completely flip that on its head. They aim for eventual consistency. They are non-blocking, which means they're fast, and they are built for massive scale. So here's how a Saga works when everything goes right. The order service does its thing, commits its work. Done. Then it tells the payment service to go. It does its thing, commits, done. Then inventory. Each step is its own separate local transaction. There is no global lock, there is no waiting around, it's fast and efficient. But here, right here, is the absolute magic of the Saga pattern, what it does when things go wrong. So let's look at our example again. Order service succeeds, payment service succeeds, but then, bam, the inventory service fails. The whole system doesn't just get stuck. Instead, the Saga kicks into reverse. It executes what we call compensating transactions. It tells the payment service, hey, run your refund operation. And it tells the order service, hey, run your cancel order operation. It gracefully cleans up its own mess to get the system back to a consistent state. And this is the core idea, the big mindset shift. Sagas don't pretend that failure isn't going to happen. They are built on the assumption that failure will happen. A Saga is basically a pre-planned, automated recovery plan that kicks in when things go sideways, and it does it all without bringing the entire system to a grinding halt. So, how did giant apps like Netflix and Amazon stay online? They do it by accepting a really profound truth about the world. Failure is inevitable. The strongest, most scalable systems out there aren't the ones that never break. They're the ones that are designed from day one with the expectation that things will break, and they're built to recover from it gracefully, automatically, and elegantly. That's the real secret.